In the previous video, we basically derived these two major equations of the kinetic molecular theory that relates microscopic properties to macroscopic properties. Okay, so the component on the left part of this is what we call the microscopic quantity. So this is the average speed of a gas particle, the root mean square velocity. Of course, we can't really go out and measure how fast things are, but what this equation allows us to do is to use things like temperature, which is something we can measure. That's why it's called a macroscopic property. And we can relate that back to something that's microscopic property, the speed of molecules. And so by using this equation, we can then get at what is the average speed of, let's say, a collection of helium gas, for example, 1 mole of helium gas. Okay. And the other important equation, of course, is the kinetic energy equation that tells you that in 1 mole of a gas, the kinetic energy is 3/2 times R times temperature. And so pretty much the temperature is related to the kinetic energy. Now, before we go on to actually do a sample calculation, I want to point out the importance of this idea here, because you see here that the kinetic energy of a gas particle is really just proportional to its temperature, right, by this R constant right here. So the question then that's useful to ask here is, we measure temperature every time and we say, well, it's 70 degrees Fahrenheit outside. What does that mean? What are we measuring in terms of the molecular property? And this equation tells us that what we're measuring is the kinetic energy of that sample of gas. Basically, what we're saying is that at a relatively hot day, or if we have a sample of gas that's hot at a high temperature, then it's a very high kinetic energy, which means the speed on average will be very high. Whereas at a lower temperature, kinetic energy is lower, which means the speed will be lower. Okay? Temperature is measuring this motion of particles. Equation. This kinetic energy here is often called thermal energy of gases because it's really the energy that's associated with temperature. The reason for this value of temperature is because there's some thermal motion that generates this heat, okay, that's observed for a particular sample of gas. The value of T, remember, is in the Kelvin scale, so the lowest number temperature can have is 0. So if the lowest temperature this thing can have is 0, that pretty much means that at any kind of temperature we're doing an experiment, 25 degrees Celsius, which is about 298 Kelvin, right? So at that particular temperature, there's quite a bit of kinetic energy. Even if you think about going to something like a liquid nitrogen temperature, about negative 180 degrees Celsius, for example, you still have quite a bit of kinetic energy. So things that you think of are frozen, they're really not. They're still moving. Particles are still moving even at very low temperature. So that's a very meaningful conclusion you can draw out of this equation, is that things are moving even at very, very low temperature. The rest of this video I just want to use to work through this particular example of just using those formulas that we talked about earlier to solve a couple of problems here. And the problem is fairly straightforward. It's just asking you, if you have these two gases, CH4 and N2, both of them in one case at 273, the other case at 546, which is double that, calculate in each case average kinetic energy and RMS velocity. To work through this problem, you just have to really remember these two equations. They're important here. First is the equation for the average kinetic energy, which is 3/2 RT, and the other one is the equation for your RMS velocity, which is just square root of 3 RT over M. And then using these two equations would be able to answer this question. I think there's a little typo here. I'm not sure why this number 20 show up here. But in any case, let's go ahead and do the calculation. This is for CH4 at 273 Kelvin. You'll find that the kinetic energy expression is just 3/2 RT. The only thing to remember, of course, is the R here has the following unit, joules per mole Kelvin, and it has a value of 8.314 when it's expressed in that unit. And then the temperature is 273 Kelvin, so the kelvins cancel out together, and what you get at the end would just be a value of about 3404.6 joules per mole. Okay, so this would be the energy of a mole of gas at 273 Kelvin. Now you notice that it doesn't really matter whether you're calculating this for CH4 or nitrogen, because we're going to get the same exact number, which is this number right here. And really, this goes back to that idea that I was asking you about in the simulation about Dalton's law, which is, why is it that when we have, obviously two different types of gases and they have different sizes, right? The size of this is smaller than the size of this molecule. Why is it that they have the same pressure? This is really the same question. Why is it that they have the same energy, kinetic energy? Okay. And the answer, of course, is that the bigger molecules, they tend to move a little slower. So the impact that they put in balanced out, even though they have a bigger mass, they tend to move slower. So then the kinetic energy then balanced out with something that's smaller smaller but moves faster. Okay, so that's the idea that I was trying to highlight also in that Dalton's law discussion with using the simulation. Okay, so this is the same concept here being repeated again. You can do the same calculation for kinetic energy at 546 Kelvin if you plug in those numbers again, but at 546 Kelvin you should have 6809.2 joules per mole, okay, as your answer. Now we're going to go ahead and calculate the RMS velocity. So I'm going to do RMS velocity on this side. Just remember, this is the formula for RMS velocity where m is the molar mass of the species. So now you have two different gases, CH4 and N2, so you're going to have different molar masses. Let's try this first for U RMS for CH4 at 273 Kelvin. Okay, so then what you need to do is take a square root of 3 times R. Now remember, R is 8.314 in this case, joules per mole Kelvin, but I want to actually write out the joules. The joules itself is, remember, is kilogram meter square per second square. That's joule. And then this whole thing is per mole Kelvin. That's R. This part here is R. Then we multiply that by the temperature, which in this case is 273 Kelvin. That's the numerator. Divide that by the molar mass of CH4. Now, if you look up the periodic table, you say the molar mass of CH4 is 16 grams per mole. But if you write 16 here, the mass unit doesn't cancel because the joules unit has a unit of mass of kilograms. So you want to convert this to kilogram to make sure that those units will cancel. So I would write this as 0.016 kilograms per mole and then carry out the calculation. You notice that these units now cancel. Kilograms cancel with kilogram, kelvins cancel with Kelvin, and then mole per mole cancel per mole. We're left with just meter square over second square. And if you take a square root of meter square per second square, what you get, of course, is just meters per second. And in this case, at 273 Kelvin for CH4, you should get a speed, RMS speed of about 652 meters per second. Okay, now I want to point out, by the way, that it's important to pay attention to this unit because I've seen many mistakes by students where they just forget to convert this and then they get a speed that's actually quite a bit lower than expected. This is actually a fairly high speed, and that's what you should keep in mind, is that the speed is very high. Now, if I were to convert this to miles per hour, this is our common measure of speed for things that we can observe, like cars, for example, and you can do a little unit conversion here by miles to meters and then seconds to hours and so on. You'll get a number that's about 1458 miles per hour. Okay, there's not a lot of things that move this fast, right? So your car at the most can go, what, 100 miles per hour before you get caught by the cops. So this is really a fairly high speed. Think about it. It's the average speed of a gas particle, okay, CH4. Now, you can do the same calculation here for all the rest of them, for all the other gases. I'm just going to list the numbers here, the answers, so you can, verify your calculation. So if you were to do the URMS for the nitrogen, in this case, at 273, what do you expect the number to be in comparison to the 652? Well, what you have to realize is, again, going back to the actual formula, the formula is 3RT over M, right? So the only thing that changes here is the M, because the temperature is the same. So then what is the molar mass of this compared to CH4? Well, N2 is a heavier particle. It's 28. This is 16. So then because it's heavier, it's going to travel a little slower. So I expect a slower speed. So in fact, if you calculate this, what you get is something around 493 meters per second. This is at 0 degrees Celsius. You can imagine how fast things are moving. This is at, again, 0 degrees Celsius, the freezing temperature of water. Okay, you can do the same calculation as I said earlier at the second temperature, which is double, I should say, the original, the 273. So it's 546 Kelvin. When you do that, the number you get here is about 923 meters per second for the methane. And if you do that for the nitrogen, you get a number that's at 546 Kelvin here. You get a speed that's a little bit slower, which is 697 meters per second for the speed of nitrogen at 546 K. Okay, so this gives you a little overview of what we did there in terms of calculation. Here we start with the kinetic energy calculation, then we went on to do the URMS calculation. But again, a couple of things I want to point out. Make sure you keep the correct units here, especially for the speed calculation, because that's the one where people made the most mistakes in. But also to remember that this is really fast. They're going at very high speed, okay? And that's something to think about later on, as far as, well, if they're going so fast, how come we don't really smell a gas very quickly, right? If it's going that fast, then you would imagine that things would, the gas will get to you in a fraction of a second, but we know that doesn't happen. So the question is why?